What if I told you that the secret to sending messages across the solar system, well, it might be hidden in a pattern that looks like it belongs on a quilt? Today, we're going to unpack a mathematical idea that connects a few simple tiles to some of the deepest, most profound structures in all of mathematics. Let's dive in. Everything starts right here with this simple-looking 4x4 grid of tiles. At first glance, it's just a nice decorative pattern. But as we're about to see, this specific arrangement holds a surprising and, you might say, inescapable order, a hidden blueprint that connects it to some truly mind-bending ideas. All right, section 1. We're calling this a deceptively simple pattern because, well, it all kicks off with this very basic 4x4 grid. We call this the diamond figure, or just D for short. It's made of 16 square tiles, and each one is split diagonally into 2 different colors, like black and white, or in this case, black and cyan. The way they're arranged is super specific, and it creates this very distinct diamond-like pattern. It's kind of elegant, right? Almost like a piece of art. Okay, section 2. This is where things get really interesting. We're calling it the surprise of inescapable symmetry. So what actually happens when we try to scramble this thing up? So imagine we can just go wild with it. We can shuffle the rows any way we want. We can shuffle the columns. We can even take those 4 little 2x2 blocks, the quadrants, and swap them all around. So how many different ways could we possibly mess this thing up? Well, the number of ways you can rearrange it, it's just huge. It's not a few hundred or even a few thousand. It is 322,560 distinct ways to shuffle this little grid. Now, you'd think with that much scrambling power, you could just make a total random mess, but that's not what happens, not at all. And this really gets to the heart of the puzzle. So on one side, you've got our original pattern, D. On the other side, one of those scrambled versions. And you see, it's not just a random jumble of tiles, it's another pattern. It has a different kind of order to it. And the big question is, why? And that brings us right to the core claim of the theorem itself. It says, with no doubt whatsoever, that every single one of those 322,560 possible scrambled images will have some kind of symmetry. Every single one. There are literally no exceptions. It's an unavoidable, inescapable property. So what kind of symmetry are we talking about? The theorem guarantees you'll get one of 2 types. First, there's what you'd call ordinary symmetry. This is the one you already know, right? Like if you could fold it down the middle, either vertically or horizontally, and it's a perfect mirror image. The second kind is a bit sneakier. It's called color interchange symmetry. That means the pattern stays exactly the same if you just swap the 2 colors. So if you flipped all the black tiles to cyan and all the cyan to black, you'd get the same design back. The structure is so strong, one of these 2 things has to be true. Okay, on to section 3, the hidden geometric blueprint. So this, inescapable symmetry, it's a huge clue that there's some kind of deeper structure going on, something that's stopping it from ever becoming truly random. Let's go find it. And this is where the chaos just starts to collapse into beautiful order. We start with over 300,000 ways to scramble the grid. But get this. A whole bunch of those scrambles actually produce the exact same final pattern. When all is said and done, there are only 840 unique designs. And the rabbit hole goes deeper. Those 840 patterns can be sorted into just 35 distinct families. That's not chaos. That is a system. So what's the deal with these 35 families? What's the organizing principle here? Well, the answer is going to take us out of the world of tiles and into a really strange, really cool area of abstract math. The secret is this thing called PG32. Now, the best way to think about it is as a kind of digital geometry. It's a whole 3D space built using only 2 numbers, 0 and 1, a completely binary universe. And the rules are weird. For instance, in this world, 1 + 1 = 0. And here's the kicker. Inside this tiny universe, there are exactly 15 points, and, you guessed it, exactly 35 lines. And this is where it all clicks together. Remember those 35 families of tile patterns? They correspond perfectly to the 35 lines in that abstract digital space. The structure isn't just similar, it's an identical match. It's a perfect mirror. Even these diagrams, which are kind of like structural X-rays of the patterns, they map directly onto the 15 points of that space. Our tile pattern is a physical object that's behaving according to the rules of a hidden digital geometry. So this discovery is already pretty wild, but the rabbit hole goes way deeper. This is where we go from simple tiles to deep space. It turns out this same underlying geometry, these 35 structures, also show up in a tool called the Miracle Octad Generator, or MOG for short. It's a tool, a really powerful one, that mathematicians use to build and understand some of the weirdest, rarest structures that exist in mathematics. And the MOG is our gateway to understanding one of these super rare objects, the Mathieu group M24. Now, this is one of only 26 sporadic simple groups. Think of them like mathematical unicorns. They don't fit into any of the neat, predictable families of things. They're just exceptions. And M24 is one of the most legendary of them all. So let's just step back and look at this insane chain of connections. You start with a simple quilt pattern. That pattern has a certain kind of symmetry, a transformation group. It turns out that group is a key piece of this thing called the Miracle Octad Generator. The MOG, in turn, helps us build one of the rarest things in math, the sporadic group M24. And M24? Well, M24 is the mathematical heart of the Golay code. That's the error-correcting code that let the Voyager probes send back clear photos from the absolute edge of our solar system. From a quilt to Voyager. Just wow. All right, last section, order hiding in plain sight. So that journey, from a tile all the way to Voyager, is just mind-boggling. And it just goes to show you the incredible reach of an order that was hiding there the whole time. And this isn't just about space probes. This same hidden geometry pops up all over the place. We're talking about building puzzles like orthogonal Latin squares. It shows up in signal processing, even in a clever type of cryptography. And then, of course, it brings us full circle, right back to where we started. Graphic design and actual quilting patterns. And one of the coolest insights is how it looks at these things called Latin squares. Now, normally, the idea of two squares being orthogonal is a pretty abstract algebraic idea. But when you look at it through the lens of this diamond theorem geometry, it becomes something you can actually see. Basically, two squares are orthogonal if their matching lines in that digital space are skew. Think of it like two airplanes flying at different heights on totally different paths. They're in the same sky, but they will never, ever cross. It's this beautiful shift from pure algebra to visual geometry. So at the end of the day, what the diamond theorem really shows us is that something as simple as a pattern of tiles can be the key that unlocks this massive, interconnected world of math. It's proof that the rules controlling a few little squares can be the exact same rules that define the rarest objects in the mathematical universe and even help us talk to probes billions of miles away. And that leaves us with a final thought. If such deep and elegant structures are hiding just beneath the surface of a simple 4x4 grid of tiles, what other profound symmetries and hidden geometries are waiting to be discovered in the patterns we see all around us every single day?